Okay, so to finish this material on measure theory, we're going to look at how you show that there is a non-Lebesgue measurable set, which will also be a non-Borel set as well, because every Borel set is Lebesgue measurable. Now, you don't have to do this to get a non-Borel set. In fact, you can prove that the number, cardinality-wise, of Borel sets is the same as the number of real numbers. And there are an awful lot more subsets of the real numbers than that. So you can get immediately, just by a cardinality argument, that very few subsets of the real, cardinality-wise, a negligible number of subsets of the real line are Borel sets, because the number of Borel sets is just the number of points in the real line, and the number of subsets in the real line is much bigger than that. The fact that any set you ever write down turns out to be a Borel set has got nothing to do with it, right? Most sets are not Borel sets, but you'll just never meet one of them. And Lebesgue measurable is even worse. Lebesgue measurable, unless you use the axiom of choice somewhere, everything could be Lebesgue measurable. But if we use the axiom of choice, then we will get some sets that are not Lebesgue measurable. Oh, and there are some explicitly defined non-Borel sets around in the literature, but we won't worry about those. Now, according to Wikipedia, Vitali did this in 1905. So it's over 100 years ago now. And it looks very innocuous. We're going to define an equivalence relation on the unit interval by saying that two elements of the unit interval are related if their difference is rational. Now, it's really easy to check that that's an equivalence relation. Obviously, x minus x is 0, so x is related to x because 0 is rational. X minus y is rational if and only if y minus x is rational. And transitivity, oh, lost my pen. Transitivity is because the sum of two rationals is rational. So it's an equivalence relation. It partitions the closed unit interval into equivalence classes, because that's what equivalence relations do. The equivalence classes themselves are basically translates of the rationals intersected with 0, 1. So that each equivalence class is countable in itself. So if you look at any one of these equivalence classes, it's only got counted any elements. What does that tell you about how many equivalence classes there must be in the closed unit interval? If each of them is countable, if each of the equivalence classes is countable, how many equivalence classes are there going to have to be in order to get, roughly speaking? Uncountably many, that's right. If you had only countably many equivalence classes, then you'd take their union, would be a countable union of countable sets, would be countable. But the closed unit interval isn't countable, so as we know by Cantor's argument. So there must be uncountably many equivalence classes. So there's the first thing. We don't seem to have done anything much yet, but there are uncountably many equivalence classes in here. And what we're going to do is take 1 point from each. Each of these equivalence classes has got infinitely many points in. So there's plenty of points to choose from. All you have to do is take 1 point from each. That sounds harmless enough. But in doing so, you've used the axiom of choice. All you have to do is believe that if you've got infinitely many sets, each of which has got infinitely many elements, that you can find some set, and they're disjoint as well, remember. The equivalence classes don't overlap each other. All you have to do is choose 1 point from each. Seems reasonable that you should be able to find a set like that. But you'll never meet that set in the real world. Otherwise, you'll have prove something almost as good as the axiom of choice. You'll never actually come across this set in the real world. This set is really nasty. Right. So there's your set E, exactly 1 point from each equivalence class. There's uncountably many of them, so this is an uncountable set, but it is a weird uncountable set. It translates by rational numbers don't meet each other. That's the first thing. No matter how you translate it around, well, they can't, because if two of its translates met each other, that would result in there being two different points in your set E which are equivalent to each other, which would mean their difference would be rational. Well, or rather the other way around. There'd be two different points in E whose difference was rational, and then they'd be equivalent to each other. But E's only got 1 point from each equivalence class. So none of these translates overlap. I'll leave it to you to check the details of that. Also, any y you take in the closed interval is equivalent to something in E. I'll do this one. Y in 0, 1, and E has 1 point from every equivalence class. So there is an x in E, which is equivalent to y. But then y minus x is rational. And call it Q. Of course, x is in E. Y is equal to Q plus x, which is one of the elements of Q plus E. But there's a little bit extra, I said up there, just a tiny bit extra. What did I say? I said that Q was rational and was between -1 and 1, inclusive. We might be able to do slightly better than that. Why is Q between -1 and 1? Well, Q is y minus x. X is in E. E is a subset of 0, 1. Y is in 0, 1. So if you take the difference of the two numbers in 0, 1, you get something between -1 and 1, right? Okay, so that did that bit. I left one little bit in there as an exercise, the fact that the translates were disjoint. But that's again, that's just for the reason that there's only one point from each equivalence class in it. Let's call the intersection of Q in -1, 1 S, just to save a bit of writing. That's just a nice countable set, and they're the translates we're going to be using. And I'll use a sequence to use them up, just so that we know we're taking a union of a sequence. But if you want to, if you're happy working with just countable unions anyway, then we didn't have to do this. But just so that I can put it into the obvious sequence form, so that we can use our measure and how to measure stuff in the usual way, let's form a sequence which goes through the whole of S, every point mentioned exactly once in the sequence, since it's countable. And now we look at all these translates, the ones we mentioned a moment ago, all the Q plus E's where Q is in S, which you could also write as union of the QK plus E's. And as we said a moment ago, any y in naught 1 is in one of these translates. So what that tells you is that the closed interval naught 1 is a subset of this union. So that's just from above. What about this one? That A is a subset of minus 1, 2. Well, E is a subset of naught 1. And now you're going to look at translating it by numbers between minus 1 and 1. So you can't escape from the closed interval minus 1, 2. So that's what's going on there. We've got A is sandwiched between two sets. So we know what lambda star does, roughly speaking. Lambda star is monotone. Whatever lambda star of A is, it's going to be between 1 and 3. Because the length of this interval is 1, and the length of this interval is 3, and lambda star is monotone. So lambda star of A has to be between 1 and 3. Now we're going to see, well, so far everything is just true. What we're going to do now is get a contradiction by assuming that it's measurable. So this is what I just said. 1 has to be less than equal to lambda star of A, has to be less than equal to 3 by monotonicity. Also, those translates have all got the same lambda star, the vague outer measure, as the original set. Translates have got, we know that translates doesn't change length, or even this generalized notion of length that lambda star does. Now we're finally going to make an assumption to get a contradiction from. Let's suppose that E is Lebesgue measurable. Then the translates are Lebesgue measurable too, because that's one of the properties we said about Lebesgue measurable sets. They're Lebesgue measurable and they're pairwise disjoint because they're translates by rational numbers. We know that no two rational numbers will give you an overlapping translates of this weird set E. That's how E was chosen. Exactly 1 point from each equivalence class. So translating by different rational numbers can't lead to overlaps. And that means you can add up. Adding up is because lambda is a measure. And we're talking Lebesgue measurable sets now. In fact, if you go back and look at this afterwards, the conclusion is that lambda stars definitely don't add up for these correctly. That's what we're going to prove in the end, because we're about to get a contradiction. The lambda stars do not add up correctly for these. If you assume they're Lebesgue measurable, then they should. Lambda and lambda star would agree, and the Lebesgue measures should add up correctly. But there is a problem. It's supposed to be coming out as something between between 1 and 3. But we're adding the same number together infinitely often. Now, think of that. Imagine that number is 1. Then what you're doing is 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, and you should get infinity. On the other hand, if the number is 0, then you're doing 0 plus 0 plus 0 plus 0 plus 0, and you get 0. And you think about it just a little bit, it doesn't take you long to realize that you've either got to get 0 or infinity if you add the same number to itself infinitely often. This is a problem because it's supposed to be between 1 and 3. Okay? So if it's either 0 or infinity, it can't be between 1 and 3, and that's your contradiction. Conclusion? Conclusion 1 is that E is not Lebesgue measurable. Conclusion 2, even without that, that set E, the lambda stars definitely don't add up correctly on, and that lives on outside the contradiction argument. So lambda star goes wrong when you add them up there. You can also prove that lambda star must be positive for that set, because in fact, if lambda star set is 0, then it's counted as subadditive, and you've got everything would have to be 0 again. So you can prove it must have positive lambda star, disjoint translates, which should also each got positive lambda star, but the lambda star of the union is no more than 3. So very much the lambda stars don't add up correctly. So you can't come up with any good way to define a total length for this set that works with translation and adds up correctly on these translates and so on. If you've got the kind of properties we're after, it's hopeless. So either really horrible set, much worse than anything we've met before, and the existence of such a horrible set requires the active choice, so it's guaranteed to be a really horrible set that you'll never meet in the real world. Then if you want to work with area, you can just take E cross 0,1. You could probably use E cross E as well, but E cross 0,1 is a bit more obvious, which gives you the sort of a vertical line at every point of E, and then the translates will cover the unit square, and you get exactly the same problem working with area. So area has problems too, for just E cross 0,1, and then you can go for volume as well, and so on. And finally then, some optional reading. We've just done measure theory and we didn't do integration theory. Integration theory is where the measure and integration gets really good, but it's another huge chapter, which we don't have time for, because we want to do some functional analysis in this module. We could throw out the functional analysis and do integration theory instead, but that's not the plan. So if you want to find out about integration theory, there are lots of books you can look in. Rudin complex analysis, or the chapter 4 of my measure and integration stuff, which is available online with audio. So there's lots of different ways you can find out about integration theory. And there you can find out about the monotone convergence theorem and Fathi's lemma and the dominator convergence theorem and great stuff like that. And finally find out how to integrate the characteristic function of the rationals and get 0, which the Riemann integral can do. And the Lebesgue integral says, well, the Lebesgue rank of the rationals is 0, so the integral of the characteristic function of the rational is 0 too. And that's it. In fact, line 1 of the definition of the Lebesgue, essentially the very first bit of defining the Lebesgue integral immediately gives you that the characteristic function of the rationals integrates to 0, and you've finished. And that was the one that the Riemann integral couldn't do. So that's got to be a good sign when the theory of Lebesgue integration gets you to solve the characteristic function of the rationals instantly. So I highly recommend that you find out about the Lebesgue integral as a very interesting study, but we've reached the end of this topic as far as this module is concerned. So we'll stop there for today.